Hi everybody, and welcome to our first unit on gas laws. And in this unit, we are going to be talking about how temperature and pressure impact the volume of gases. So we're going to do this by talking about several different gas laws. And the first one we're going to talk about is what's known as Boyles Law. All right, Boyles Law shows the relationship between volume and pressure. For Boyles Law, your temperature is going to remain constant. Also, another note, the number of particles are going to be constant. Number of particles are going to be constant for this entire unit. We'll change those a little bit in the next unit, but for all of the gas laws we deal with in this unit, your amount of your actual gas, your number of molecules does not change. So again, Boyles Law shows the relationship between volume and pressure, all right, of a gas. Okay, so as volume decreases, so you can imagine you have a container and it is getting smaller, you will have less space for the particles and there will be more collisions with the sides of the container. All right, because you get more collisions, you will have an increase in pressure. So again, as volume decreases, you have less space for the particles and there's going to be more collisions. So therefore, there is an increase in pressure. So as volume decreases, pressure increases. So we say that this is an inverse relationship. All right. Now, there's a couple ways that we show this. And the first is just to show the mathematical relationship. And this is an inverse relationship. K, the small k, is constant. All right. So if this number is going to be constant, if V goes down, P has to go up, right? We know it's our basic algebra skills. As one goes one way, the other must go the opposite. So this is an inverse, all right, relationship. Now, I also have what are known as the useful equations. And by that, I mean, this is going to be the one, and that's why I made it such a huge font. This is going to be the one that you're going to be using when I ask you to do some calculations. And this is V1, P1 is equal to V2, P2. Now, what do I mean by 1 and 2? So 1 are your initial, all right, volume and pressure, and 2 would be your final. So when I use the number 1, that means initial, or what you are starting with, all right, and 2 is your final. Okay, so let's take a look and see what these are going to look like. All right, so here are some practice problems. 250 milliliters of a gas at 150 kilopascals is moved to a volume of 150. What is the final pressure of the gas? All right, so we know our equation for Boyles Law is V1, P1 is equal to V2, P2. I like to do my algebra before I put my numbers in. This is just a preference of mine. You can really do it however you'd like. All right, so what is the final pressure? That's what I'm looking for. So I'm looking for P2. So P2, okay, what I'm gonna do to get P2 all by itself, I'm gonna divide each side by V2. Okay, so P2 is going to be equal to V1, P1 over V2. Again, how you decide to do your algebra is completely up to you. You have 250 mils, that's your initial volume. So that goes right there. All right, and your initial pressure is 150 kilopascals. You are changing that volume to 150. So you are decreasing that volume. Sorry, this is not kilopascals, that's in milliliters. All right, you're decreasing that volume. So what should happen to the pressure? The pressure should go up. Remember, it's an inverse relationship. All right, and mathematically, this is really nice because it just kind of works out this way. This was not intended, but your 150 do just divide out. But also, please make sure that your units divide out. Milliliters divide out, which means you are left with a final answer of 250 kilopascals. All right, nice and straightforward. All right, so let's take a look at number 2. Feel free to pause the video and you can do this on your own if you'd like to. Correct, and when I say correct, I just mean change 333 milliliters of gas at 199 kilopascals to the volume it would occupy at standard pressure. Okay, so again, I am using my V1, P1 is equal to V2, P2. But now I need, all right, correct this gas at this to the volume. So I'm looking for V2. Okay, to get V2 by itself, I'm going to divide each side by P2. So it's going to be V1, P1 over P2. My initial volume is 333 milliliters. My initial pressure is 199 kilopascals. And my final pressure, all right, to the volume it would occupy at standard pressure. Standard pressure, remember in kilopascals from the last unit, is 101.3 kilopascals. All right, your kilopascals are going to divide out. You'll be left with milliliters, which is a volume unit, and that's what we want. All right, you're going to punch that in your calculator, and you get about 654 milliliters. All right, great. Okay, so those were Boyles Law problems, and let's make sure that this makes sense. What did you do to the pressure? It was 199. All right, you took it down to 101.3. So the pressure went down, therefore the volume should go up, and it went from 333 to 654. So the answer made sense, which is great. All right, so now let's talk about our next gas law, which is Charles's law. Charles's law shows the relationship between volume and temperature. This time, your pressure is going to remain constant. All right, here we go. As temperature increases, the particles move faster. And this is the important part. And in order to keep the pressure constant, which we have to for Charles, all right, the volume must increase. Okay. All right, and the best kind of thing to think about with this is think about a balloon. All right, a balloon is a container that allows for the volume to change. All right, so as the temperature is going to go up, those particles are going to move faster, right? They're going to move faster and faster. If the pressure inside has to stay the same, then that balloon has to get larger and larger. And that's what balloons do until they reach their maximum, and then they will end up popping. So as temperature increases, volume will increase or has to keep pressure the same. This is a direct relationship, okay? And we show this, and you need to write this in because it didn't type in properly, with this equation, V over T is equal to K. All right, so remember K is a constant value. We're just showing the relationship here. So as T goes up, V must also go up. This just shows that direct relationship. All right, the useful equation, again, and I have it in a huge font, all right, is V1 T2 is equal to V2 T1. Now, I like it this way because I like things all in the numerator, but some people like to write this equation, and either one is totally valid. They like to keep their volumes on one side, so V1 over V2 is equal to T1 over T2. Okay, which is, again, totally fine if that's the way that you'd like to do it. I tend to like this first one better, but either one is totally valid. All right, now, please keep in mind, okay, and I mentioned this during the last unit, but please keep in mind, when we are doing calculations for gases using temperature, we always have to convert the Celsius to Kelvin. Always, always, because remember, Celsius has zeros and it has negative numbers, and algebraically that's just not going to work out really well. So we're always going to have to convert that temperature to Kelvin. All right, so let's take a look. Okay, before we get started on some practice problems, just a couple reminders. Standard temperature is 0 degrees Celsius. So if I were to mention standard temperature, that is 0 Celsius, which remember, to go from Celsius to Kelvin, you just add 273. So 0 Celsius is 273 Kelvin. When you see the abbreviation STP, that stands for standard temperature and pressure. So just a little reminder before we move on. Okay, so let's take a look at these practice problems. What will be the volume, all right, of 100 milliliters of a gas if its temperature changes from 125 to 10 degrees Celsius? So first off, let's remember our equation. V1 T2 is equal to V2 T1. Again, I like it looking this way, so I'm going to do my problems this way. All right, so what will be the volume? So I'm looking for my final volume. I like to do my algebra first. So I want V2 by itself. So I'm going to divide each side by T1. All right, so V1, T2 over T1. Okay, so now it's time to plug in some numbers. My initial volume is 100 milliliters. Be careful, my final temp, because that's T2, my final temp is 10 degrees Celsius. So 10 plus 273, that's 283 Kelvin. My initial temperature, all right, is 125 degrees Celsius. So 125 plus 273 is 398 Kelvin. You're just going to plug those in. Your kelvins divide out. You're left with milliliters. That's what you want. And you get a final answer of about 71.1 mils. Okay. And again, if you look, what did we do to the temperature? It went down in order to keep the pressure the same. What should happen to the volume? It should go down, and it did. All right. Feel free to pause as we go over. Pause the video and you can do this next one on your own if you'd like. All right, here we go. So 500 mils of a gas at standard temperature is compressed to 500 mils of a gas at standard temperature is heated to 200 degrees Celsius. Okay, what is the new volume? All right. So let's see what we're doing here, okay? So new volume, I am looking again for V2. So it's gonna be the same setup as above. Okay, my initial volume is 500 mils. All right. My final temperature, because this is T2, okay, my final temperature is 200. So 200 plus 273, right? So that's 473 Kelvin. And my initial temperature, I told you I had 500 mils of gas at standard temperature. Remember, standard temp is 273 Kelvin. So I'm going to go on ahead. 500 times 473 divided by 273. And I get 866 milliliters, okay? And again, you have, it was at standard. It went to 200 degrees Celsius. So you increase the temperature, you should see an increase in volume, and we see this. All right, great. So you should have one more like this in your notes, and that again is number 3. All right. You can take a second and pause the video and do this on your own if you'd like. Okay, and we will do this together. All right, what will be the volume of a balloon if at 25 degrees Celsius the volume is 500 mils and the temperature is changed to 35 degrees Celsius? So again, we are looking for volume again. All right, I don't know why I made all these sample ones looking for final volume, but that's okay. All right, over T1, so same as before. Okay. Okay, so we're going to start punching in our numbers. So we are looking for our initial volume. Okay, so here we go. Initial volume, initial temp, final temp. So initial volume is 500 mils. Okay, then I have my final temp, and my final temp is 35. So 35 plus 273, because we remember we always have to put these into Kelvin, and that's in Kelvin. All right, and then its initial temperature, this initial temperature was 25. You're gonna see 25 degrees Celsius show up a lot because that is room temperature. So just so you know, if you start seeing 25 Celsius a lot, that's why. All right, so 298 Kelvin. So we're gonna go 500 times 308, enter, 500, 308, yep, divided by 298, and that gives us about 517 milliliters. Okay, all right, temperature went up. We expect the volume to go up, and it did. Okay, fantastic. So, two more gas laws to talk about today, and they are just a continuation of what we've already talked about. All right, so we have Gay-Lussac's law, which shows the relationship between pressure and temperature. In this case, the volume is constant. All right, and this is also a direct relationship. Okay, so Gay-Lussac's law describes the relationship between pressure and temperature, assuming that your volume is constant. So for this gas law, you want to think of like a metal cylinder where the volume will not change. As you increase the temperature, those gas particles are going to be moving more. They're going to be hitting the sides of the container more, and that pressure is going to be getting higher and higher. Eventually, if that continued, the container will not be able to hold that pressure, and the container would actually explode. And that's what happens in the case of many types of bombs. Okay. All right. And then finally, if we put together Boyles Law, Charles's Law, and Gay-Lussac's Law, we will get what is known as the combined gas law. And what's nice for you is this is really the only equation you need to memorize because this combines all three gas laws that we've talked about today. And here's the equation. P1 V1 T2 is equal to P2 V2 T1. So if you just remember this one, you're going to be all set because let's say you come across a problem and they don't talk about temperature. Well, you just, okay, take that out. No temperature. All of a sudden, I'm Boyle's Law. Okay. And it's going to be the same for any variable that is constant. Or if I change a bunch of the variables, you are going to use this one. All right. So again, I like things on one line, and that's the way we write it. You could certainly write it, okay, as this. Some people like all their initials on one side. So P1 V1 over T1 is equal to P2 V2 over T2. Either one of these is perfectly valid. All right. But this is our combined gas law, the one we will be using a whole lot in our next set of practice. Okay, have a great day, everybody.